Good morning. Good morning to all.
Good morning, sir.
Morning, sir. Good morning, sir.
Um, so let us start. So last class we have discussed this filter. Please recall this is the partial filter. Uh, it is two types: smoothing and sharpening. Uh, and smoothing is a low pass filter, which is further divided into linear filter and non-linear filter. We have already discussed the linear filter. Please recall the linear filter uh, is nothing but the particular pixel is a pixel value. And pixel value means it is gray level value is replaced by the average pixel value of its neighbor, the mean value of its neighbor filters. So that is why it is called the linear filter. So uh, so uh, similarly, the non-linear filter is median filter. It is same as the mean filter. The only difference is the mean filter, which is calculated by the taking the mean or average of the its neighbor or pixel. Now it's take the in place of mean, it takes median. And it has some advantages we have already discussed. The excellent noise reduction capability. It preserves edges. There are some problem in mean filters. It introduces less blurring than the smoothing linear filters. Linear filter has a drawback. Please recall it that is it is blurring, but it less blurring as compared to the mean filter. It is very effective in the presence of a impulse noise, but it is perform poorly in the presence of Gaussian noise. And the disadvantages is uh, if the number of pixel is greater than if the number of noise pixel is greater than the of that region is a particular region which the region we are interested to find the noise to make the filter is greater than the half of the number of pixel in the entire window, it perform poorly. And also it perform poorly in the presence of Gaussian noise. We will discuss about the impulse noise and the Gaussian noise type of noise. And the steps we have already discussed. In place of mean, we have to find the median, and in order to find the median we have to make it sorted. We have already discussed. You see this is 0 is replaced by we want to find the new value for 0, and the 0 will be replaced by the median value of its neighbor, that is 3 7 2 1 0 0 9 5 8. And in order to find the median we have to first sorted the value, and 3 is the median value. So 0 will be replaced by 3. Similarly, the other pixel value will be replaced by its median. And finally, we get a new image after the median filter. And this is another example we have already discussed. And but besides that, there are two other type of filters, are minimum filter and maximum filter. Please recall, minimum filter removes the noise, salt noise, as the name suggests. Minimum filter, any large value of that max position will be replace the minimum value among its neighbor, and similarly the max value, max filter, which is it removes the paper noise or black dots with small gray label values, because any black dot within that filter will be replaced by a brighter one, because it takes the greatest one. You see here, this is the best example. uh, uh, the same example we have discussed in median filter, which is 0 will be replaced by 3. Please recall, because 3 was the median value, so 0 was replaced by 3 at that case. Here the same example you see. But if we apply here minimum filter, mean filter, 0 will be replaced by 0, because uh, in this window, in this region, 0 will be the minimum. So 0 will be replaced by 0. But in max filter, 0 will be replaced by 9, because in this region, 9 is the maximum value. So 0 will be replaced by 9. You see here, you can imagine here how the salt error and paper error is avoided. You see, in the minimum case, the salt error, the white point is not there, because 0, suppose 9 is the maximum, 9 is darker. So if we replace by 9, so 9 neighbor is 0, that is 9 will be replaced by 0. So it will give a black color. So no white spot is there. Similarly, in max filter, you see 9, 0 will be replaced by 9. 0 is a black color. You know that 0 is a black color, and it will be replaced by the 9. So more brighter, so the black spot will be eliminated. Black spot will be eliminated, because 0 will be replaced by 9. So 9 is not darker, 9 is brighter than 0. So another technique which is represent graphically the different gray label values, the frequency of the gray label values for a particular image. It's a graph in which two axes, x axis and y axis, is a two-dimensional graph. X axis represent the gray labels and y axis represent the number of pixels. You see, there is an image in the left side, and this is the corresponding gray label value, which is given in a matrix form. This is a tabular form. Black color is represented by 0. 1 is represented by another black color, but it is not darker than the 0. 2, 3, 1, 2, 3, 2, 4, or 9. 6 is the maximum value. And you see, there will be a graph for RK. RK is the gray label value. NK means the number of occurrence. You see, there are 0 occurs 6 times. So that is why the n value or nk value of 0 is 6. 1 is 1, 2 is 2, 3, 2 twice, you see, 3 ones, 4 ones, 5 none. So it is 0, you see. There is no 5 in the table. So that is why the occurrence is 0. 6 occurs 1 once, that is why it is 1. So I have can see here. and 0 6 times, you see the graph of 0, the bar graph of 0 is height is more. 1 2 3 4 5 and 6, and this is the histogram. This tells us about that how many times a particular gray level value occurs. 0 occurs 6 times, 1 occurs once, 2 twice, 3 once, 4 once, 5 none, 6 1. So this is the histogram representation of a particular region of the image. Then normalized histogram. It is obtained by dividing the frequency of occurrence of each gray label RK by the total number of pixels in an image. You can tell it is a probability. You see P of RK, NK by N. N is the number of pixels in the image. N is the total number of pixels in the image. PRK, you see, the probability of RK gives the probability occurrence of the gray label RK. What is the probability occurrence? The sum of all occurrence of a normalized histogram is equal to 1. As we know, the sum of the probability of all events of a sample space is 1. Okay, we know that the probability, the sum of probability of all event is 1. Of a sample space is 1. So here also the probability of the occurrence of all gray label value, the sum of probability must be give the 1. Okay, we know that that is the a sample space. Suppose you are tossing a coin, the probability of getting a head is 1 by 2. The probability of getting a tail is also 1 by 2. So there are two events in this sample space. The sample space is either head or tail. The maximum number of events, 2. That is, when you tossing a coin, you will get two outcomes, head and tail. There is no third option. So the number of sample space is 2, and getting a head is 1. So that is the probability of head getting is 1 by 2. Similarly, probability of getting tail is 1 by 2. If you add them, 1 by 2 plus 1 by 2 is 1. That means the sum of all the events, the sum of the probability of the events of a sample space is equal to 0. Sorry, is equal to 1. Is equal to 1. Similarly, here also you get the probability. You see, we have a second example. Find the normalized histogram of the image. So we already calculated RK NK in previous example, so there are no need to find that. We have to find only the probability. You see, probability of NK is 6 by 12, because 12 is the number of pixel in this image. You see 1 2 3 4. There is a table, original table having 3 rows and 4 columns. So total number of element is 12. So the total number of image or total number of pixel in that image is 12. So that is why 1 RK is 1 sorry, it's a 0. There is a mistake in RK value. See, the first one is 0, then 1, then 2 3 4 5 6. Mistakenly it is 1. RK value is 0 1 2 3 4 5 6. The first one is 0, not 1. So 0 occurs 6 times. You see, and the probability is 6 by 12. The probability is 6 by 12. Similarly, 1 occurs 1 times, 1 by 12. 2 occurs twice, 2 by 12. 3 occurs 1, so 1 by 12. The probability of getting 3 is 1 by 12. The probability of getting 4 is also 1 by 10. The probability of getting 5 is 0. That is, there is a impossible event. You cannot get 5 because 5 is not in the your sample space. So there is no chance getting 5. There are no pixel having gray label value 5. So the probability of this is event is 0. It is an impossible event. And probability of getting a 6 is 1 by 12 because there is only one 6, that is 6 occurs once. So that is why 1 by 12. And if you check, you can add the probability value of all the event 6 by 12 plus 1 by 12 plus 2 by 12 plus 1 by 12 plus 1 by 12 plus 0 plus 1 by 12. You will get 1. You must get 1. That means it indicates that the probability, the sum of all components of a normalized histogram is equal to 1, and it is also 1. You see, this is a normalized histogram. In a simple histogram, we have taken x-axis and y-axis. In x-axis, the number of occurrence, sorry, the gray label values, and the y-axis contain the number of occurrence, how many times. But here, there are slight difference. The x-axis represent the RK value, that is the gray label value 0, 1, 2, 3, 4, 5, 6, and the y-axis represent its corresponding probability value. You see, the probability of getting 0 is 6 by 12, that is 1 by 2. So it is, you see the height of 0, it occurs 6 times. The probability was 6 by 12, 1 by 2, and you see 1, 3, 4, and 6 all have greater value 1, and the probability was 1 by 12. So all are height, same height, 1, 3, 4, 6. 2, the probability of getting 2 is 6 by 12. You see, 6 by 12, it was 6 by 12. So the probability is no, 2 by 12, I think, 2 by 12, because 2 occurs twice. So 2 by 12, it is 1 by 6. So the probability 1 6, and 5 is a impossible event. There is no chance to get 5. So its probability is 0, and it is a normalized histogram. Let us discuss why. Why this histogram is used. Normalized histogram, general histogram, you see. Based upon histogram, we can categorize image into 4 categories, which are image underexposed image. There are picture we'll discuss. Underexposed image and is a histogram in 4B. Underexposed. It may be noted that almost all the pixels are connected at the lower end of the histogram. The maximum value of the gray label is less than 50. So it is more darker. Less than 50 means you know that no detail are seen in the image. Let us come to the image directly. The first one, figure A, is underexposed image. You see the histogram. The histogram is close to 0, and if the histogram gives this sign, so we will get an information that it is the underexposed image, and the gray level value of all pixel is less than 50. So 50 means it is more darker, it is not clear, it is more black color is there, so the details is not clear. You will not get any more information or detailed information of the image because it is underexposed image. So this is the application of histogram. From the histogram we will let to know that is it is an underexposed image because all the graphs are closer to 0. So it is a underexposed image. Then come to the second category, overexposed. There is a figure shows an overexposed image, and the histogram is also given. This histogram is prominent towards the higher side of the gray values, with the lowest gray value is around 150, and all other values greater than 150. So it is more exposed, more closer to the white color. This is opposite to underexposed image we have discussed in the last slide. And this image has a washout look because it is absent of darker shades or gray. So darker shades are absent because you know that if more than 150 is there, so it is closer to 255. So that is why it is more brighter. Let us come to the im- uh, you see the C and D. See the overexposed. And all the graphs in the histogram you see are available towards the maximum value. There is no line near the 0, no darker, no black color is there. It is overexposed. And you see the image, it is not clear. There is no darker side. So these histograms give the idea that is my image is overexposed. Then come to the third category, low constant image, E and F. In the figure you will see the shape of the histogram is narrow and centered toward the middle of the grayscale. So all the gray value are available in the middle. There is no black color, no darkest color, or no lighter color. The first one where is underexposed, all the graphs are closer to, all the lines are closer to the 0. So it is more darkest. Detailed information is not available. You will get less information because it is underexposed, and it is nearer to 0. All the pixels nearer 0. The maximum value is 50. So 0 to 50. So that is why it is underexposed image. The second one is overexposed. That is the minimum value is 150. The all other values greater than 50. Sorry, 150. So no darker side is there. So it is brightest one. Here, this is also possible problem that you will not get the detailed information because it is overexposed. Third one is low constraint, means all the lines of the histogram will present at the total middle. No darker side, no brighter sides. So all side in the middle. You see, the histogram is exactly middles in between 200 to 170, 180, like that. No image is less than 100 or 100 and low is greater than 100, 180. That is no brighter value, no darkest value, only the middle value will be shown. You see the image. This image is not clear. This is looks like a gray color. That is the middle of the black and white. It is not neither not dark or not brightest. It is exactly middle of the, so it is low constant image. So from the histogram, we are able to know that the quality of an image. So let us discuss the fourth one. You see, this is a low constant. The shape of the histogram is narrow and centered toward the middle of the grayscale. Very few gray label participate in the image formation, as neither the lower gray label nor the higher gray label are present. Thus, detail also not visible. As I discussed, as all the lines are present in a given range, minus 100 to 200 or 180, that. So that is, there is neither the uh, um, lower gray levels or higher gray levels are present. So that is why the details are not visible. You will not get the detailed information from that image. Then come to the fourth one and the best one, the high constant image. It shows a high constant image. Some figure are there. We will discuss. This histogram covers a broad range of gray level, but distribution of pixel is not uniform. The number of some gray level is very high as compared to the number of other gray levels, and they are, uh, you see, distributed uh, uniquely in there. You see the picture. Almost all gray level value present in the image. There are some black color nearer to 0. There's a pixel nearer to 100. There are some pixel nearer to 200. There are some pixel nearer to 255, a maximum value. That is uniformly distributed. You see, if you compare all the four histogram, the first one is, you see, all the lines are nearer to 0. In second one, all the lines are closer to maximum value. And third one, all the lines are available in the exactly in the middle, neither to left or neither to not to right. But the fourth one is, you see, there are some pixels where closer to 0. There are some pixels closer to high values, 255, and there are also some pixel where available on the middle, 100, 200, 250. And you compare the image, left side image, and the last one is the more prominent, and you will get the detailed one here. You will get the information from it. You can mm, get some information from it as per your requirement. So as you compare the fourth image, the last one is the more prominent. You see, so the histogram which gives this information about a picture. Application. So it is clear that histograms gives the information of an image, whether it is underexposed, overexposed, low constant, and high constant. Besides that, there are some other applications. Let us discuss. Histogram indicate if clipping is a problem in the image. We already know the clipping thresholding in the previous classes. That is, clipping is a there is a range and threshold also that there is a fixed value. If any image value or gray level value is greater than it, it map to the maximum value. Otherwise, it is mapped to zero. You will get either a black color and white color. So it is extensively used in thresholding to separate the constanting object from the background. It tells about the image constant because from that line from the bar graph would give you this information. Either it is a low constant, either a high constant, is overexposed and underexposed. So this is the application of histogram. So we know that image filtering done in two ways. One is your spatial domain, another is your frequency domain. So we have already discussed the spatial domain. Let us see how the image enhancement and filtering is done in frequency domain. In the previous unit of the course, we have considered an image in the spatial domain, which is the form of which a camera captures it. In this unit, we shall view the image as a signal and apply the well-known filtering technique used in signal processing. So it is a type of frequency filter also, smoothing filter, sharpening filters, and homomorphic filters. In spatial domain, we will use the smoothing filter also, that is the your linear filter and non-linear filter. Here, the frequency domain filter are categorized into three types: smoothing filter, sharpening filter, and homomorphic filters. So this is a block diagram of frequency domain filter, smoothing filter, sharpening filter, and homomorphic filters. Smoothing filter divided into idea, Bluetooth, Butterworth, and Gaussian filters. And sharpening filter also idea, Butterworth, Gaussian, Laplacian, and high boost. And homomorphic filters are one type. So the frequency domain filter are broadly divided into three types. So let us discuss the first filters, smoothing filters. Smoothing filters are low pass filters. LPF, edges, sharp transitions, and noise in the gray level contributes to high frequency content in an image. A low pass filter only passes low frequency and block in the high frequency one. As the name suggests filter, this filter only passes the low frequency and block the high ones. So if it blocks these high ones, it removes noise, but in the process, introduce blurring as a side effect of the image because all the high level frequency is blocked. So that is why this is a side effect. This is, you can tell, it is a drawback of blurring. So smoothing process is blur. You see here, the basic model of filtering is GUV. You will get HUV into FUV, where FU is the Fourier transform. There is a transformation we will discuss, and HUV the transverse function of the filter, and GUV enhanced image with high frequency component have been altered. Ideal filter has sharp slope in transition band, whereas Gaussian filter has, we'll discuss about Gaussian filter, has smooth slope in transition. Butterworth filter has a parameter called filter order which control the slope of the transition band. High value filter order leads to the ideal filters. Let us first discuss ideal low pass filter. Ideal low pass filter removes all frequency above a certain frequency component D0. That is, if the certain frequency D0 is given, if the particular frequency has D0 value is less than D0, it filters, otherwise it block it. That is, if you filter it, it is 1, otherwise it is 0. Ideal low pass filter is defined by the transfer function HUV is equal to 1 if DUV is less than equal to G0. Suppose the D0 is 100. So every frequency is less than 100, it will map to 1. Or every frequency is greater than D0, it block it. So its value is 0. Okay. So there is a fixed value D0, and if the frequency is greater than this, it will be 0, and if it is less than equal to 1. So mathematical function is given here, where DUV is this. So some transfer function is used. You see, you'll find an idea. You see the prospective plot of the ILF, and you will get an image of IPF will display an image with D0 equal to 10. So at the D0 equal to 10, as you know, 10 is the closer to 0. So all the pixel only pass the filter if the value is less than 10, less than equal to 10. So you will get a darker image. Darker image. You see the image which is formed by ILF, ideal low pass filter, is 0. So as it is 10, if you take more D0, suppose you take D0 value 50 or 150 or 200, so that is the output will be different. That means only it will pass the pixel value which is less than that value. So D0 is 10 is fixed. So this filter only pass the filters which is less than equal to 10. So less than equal to 10 means the darkest value. So you see the image, it is the darkest value. And you see the transform function and you see the B. That is, you will get all the information about 0 to D0. It is 0 to 10. The other value will be not be reflected because the filter will not pass it. Okay, you see there is a rectangle in figure B. There is a rectangle type of picture, that is all the image will be displayed from 0 to D0 only. So as the D0 is 10 here, we will get a darker picture. No detailed information will be available. So if the D0 value increases, that is you will get a some value, that is the image will be different. Property of ILF, as it is an ideal filter, it is non-real, non-actual, and non-physical. But it can be stimulated as a component and show low pass filter image with different cutoff frequency. So as is non-real because actually the other frequency are cut off. So we will not get the detailed information. As the filter radius increases, less and less power and information is removed, which result in the less blurring. So if we increase the value of D0, so we will get uh, less blurring image. A very noticeable effect that can be seen in the output image is ringing. What is ringing? Now, ringing is a undesirable and unpleasant lines around the object present in the image. So it is one type of noise, you can tell. It is an undesirable and unpleasant lines around the object present in the image. So there will be if we do this, that is this is a, you can tell this is a drawback of ideal filter. So there this problem is called ringing. You may get a short note what is ringing. That is ringing is nothing but it is undesirable and unpleasant lines around the objects present in an image which is not desirable. We don't want to see it because it is a noise and it the picture no, will be not clear. As the cutoff frequency D0 increases, as I discuss again and again, at the cutoff frequency of the frequency D0 increases, effect of ringing reduces. Ringing is a side effect of ideal filter. So if you increase the D0, suppose you see the previous one, it is 10. So that is why a more black color is present. If it was 100, if this is 100, you will get a more more uh, prominent pictures. More prominent picture, the quality will be increases. So there will be less blurring. It will be more clear about ILAV, ideal low pass filtering, with this figure. You see, you see the A. A is the original image, and if this is output of ILF with D0 30. So 30 is closer to 0. So the output of this filter must have ringing option. You see there are some undesirable line around the object. Please see it by making it zoom. Make it zoom and you see there are some unpleasant lines around the object and it is more darker because D0 is 30. D0 is 30 which is closer to 0. Similarly, you see the option C, output of ILF with D0 50. So 50, you know that 50 is brighter than 30. So you will get a more clear picture as compared to B. It is less blurring as compared to the 30 as the D0 value increases. So a suitable D0 value should be there to get a more prominent picture. A suitable D0 value. Similarly, you see another image, some text was written there. You see some text are written. This is the original image. You see the second one, figure 8, B of figure 8. Output of ILF with D050. Then output of ILF with D080. You see 8 is more clear than B. So if D0 increases, you will get a less blurring picture. So this is ideal low pass filter. So as the name suggests, so as a fixed D0 value. And this filter passes all the image values, all the intensity value which is less than this D0 or equal to D0 and other is blocked. So this is the output of ILF with D080. So this is all about your ILF. We'll discuss about the other filter and I have sent this slide to you for this 114 slides are there. You see, we'll discuss another, then we return. 1 minute. But before that, let us discuss another topic, 2D transformation. 2D transformation, which is known as two-dimensional transformation. As the name suggests, transformation, that is, you have to transform a object from one form to another form. That is, you may change its position, you may change its size, you may change its shape, you may rotate it, an image, either clockwise or anti-clockwise with respect to origin or any other on the other line with some degree. Suppose you have to rotate 45 degree 60 degree, 90 degree, 180 degree. You have to rotate an image according to the requirement. Besides that, you can also change its shape with respect to another. You know that as it is a two-dimensional transformation, so you can fix the size of its x-axis and increase y-axis or vice versa. This is transformation. So transformation required because we need our object to be transformed from to another. Suppose there is an image. The image you see, the image is not a particular height, and you want to change its direction. Okay, so you can change it. Suppose you want to change its position. Suppose a uh, uh, image is present in x and y location in the in a 2D platform. It is present in x and y location. You want to transform it from xy to another location, x dash y dash. We are able to do it. We can able to do it. So this is a the objective is it is a basic 2D transformation, rigid body transformation, and the first three techniques are there: translation, rotation, and scaling. We'll discuss here translation, rotation, scaling, and homogeneous representation and coordinate. What is the homogeneous representation? And a 2D composite transformation. That is, a transformation can be composite. You can perform various transformation technique in a single image. In a single image. Besides that, other transformation is there: the reflection, rotation, shearing. The reflection means your maybe your image reflection. That is when you stand in front of a mirror, you will see your image. So suppose you are in you want to know the image of an image of an object, so you can view the image. That is called a reflection image. Geometry transformation, as we discussed, it is sometimes also called the modeling transformation. Geometric transformation is changing an object position. If you change the position, if you want to the position xy to x dash y dash, that transformation is known as a translation. So using translation, you can only able to change the location of an image. Location, the position of an image. So translation is always associated with the location. Similarly, orientation, you can rotate. As we discussed, we can rotate an image for either clockwise or anti-clockwise in some degree. Suppose you want to 30 degree, 60 degree, 45 degree, 90 degree, you can able to rotate it as per the requirement. And scaling, you can change the size. Suppose the size is large, you may reduce it, or suppose the size is less, you may enlarge it. You can increase or decrease the size of the object according our requirement. Other transformation is reflection and shearing operation. We'll discuss one by one how the translation is done, how the rotation is done, how the scaling is done, shearing. We'll discuss about that. You see here, there's a first technique for the 2D geometric transformation is translation. You see the image first. Suppose we have an image at P. we have an image P, and after translation T, after translation T, the P is shifted to P dash, shifted to P dash. That means P is location at XY. Now we apply translation and that is shifted to P dash. X dash Y dash with location X dash Y dash or P to P dash. You see here the new location X dash is nothing but X plus Tx. What is Tx? The Tx is the translation value along X axis, and Y dash is equal to Y plus Ty. That is Y plus Ty. Ty is the translation value along Y axis. That means we have shifted P to P dash by adding some value in X and Y. X is added by Tx and Y dash is formed by adding it Y plus Ty. So the X dash and Y dash is the new location of that image, or you can tell it the pixel. And the matrix form you can write P dash equal to P plus T. P is the matrix XY, T is the matrix TX TY. So if we added P plus T, we will get P dash. That is X dash is equal to X plus Tx and Y is equal to T. You see, if we add matrix P and T, we will get X dash is equal to S plus T, Tx and Y dash is equal to Y plus Ty. Transformation moves the object without deformation. So transformation is only used to move from one location to another location, to shift from one location to another location. So the summary of this translation is only to move from one point to another point. So if you want to move an image from one location to another location, obviously the translation is used. Similarly, in previous example, a point is only moved. A point is moved. Suppose the image is a line. We have to translate the entire line. You know that a line is nothing but it consists of several points. So to move a line segment, apply the transformation equation to each of the two line endpoints only, and redraw the line between the new endpoint. You need not to apply translation each and every point of that line. So you have to only translate the two endpoints. Two endpoints. Suppose P and Q. Suppose P and Q are the endpoints of a line. You have to only translate P to P dash and Q to Q dash, applying the translation. After that, applying this, translating these 2 points, you have to redraw, join these 2 points. Join these 2 points, you will get a new line after translation. To move a line, similarly, to move a polygon, suppose to move a triangle has 3 endpoints, 3 vertices. So apply the translation to these 3 vertices. Suppose you have a rectangle, 4 vertices. So apply the translation to the 4 vertices. You have pentagon, 5 vertices, hexagon, 6 vertices, like that. So to move a polygon, apply the transformation translation equation to coordinate of each vertices. And after translation, you have to draw or join this line, this point with the line segment, and a new polygon will be generated. Okay, so in this way, we are not only translate a point, but also we can translate a line, or a polygon. The second one is rotation. Translation is only used to move the object from one location to another location. But rotation, 2D rotation, it rotates the axis, rotation angles, and rotation point or pivot point. We have to rotate an image to a particular direction. You see here, there is a image, and we have to rotate with the angle theta. After rotation, you will get a new image. Same image is rotated along x-axis and y-axis. So if you want to rotate it anti-clockwise, you have to take theta as positive. If theta is negative, it is a clockwise rotation. In rotation, there is another term which is associated with the pivot point. That means in which point should be fixed. That is here, basically the point is taken the origin. So the new point is calculated by x cos theta, x dash is equal to x cos theta minus y sin theta, and y dash equal to x sin theta plus y cos theta. So in previous case, x dash is equal to x plus tx and y dash is equal to y plus ty. But here you see x dash equal nothing but x cos theta minus y sin theta, and y dash is equal to x sin theta plus y cos theta. Theta is the angle of rotation. Theta here is the angle of rotation. You see, suppose the point is at xy, and we want to rotate about origin. So the pivot point is origin. And we want to rotate the angle theta. So as the theta is positive, it is clockwise. And after rotation, you see now the x dash y dash, the new position is x dash y dash, but with respect to origin. And the total angle is first it was phi, and this is theta, theta plus phi. And in matrix form, you see the two division p dash equal to r dot p, where r is equal to cos theta minus tan theta, sin theta, and cos theta. This is a rotation matrix. If we multiply r and p, we will get p dash. Initially, it was an addition. You remember that p dash is equal to p plus t in translation, but here p dash is equal to r into p. Two matrix should be multiplied here. So we have discussed that this is the rotation matrix and this is the rotation formula. So rotation of point about any specified position x or y r. X r means pivot point. Suppose pivot is maybe another point other than the origin. This is x dash equal to x r plus x minus x r cos theta minus y dash sin theta, and y dash equal to y r, that is the specified position is x r and y r. Here y r is equal to x minus x r sin theta plus y minus y r cos theta. So rotation also move object without deformation. It also moves object, but with respect to some pivot point. That is why it is not same as the translation. Translation only translate. There was no pivot point. Rotation also move the point from one position to another position, but it only rotates with respect to a pivot point. It may be origin or many other point. Similarly, as per the as exactly same as like the translation, a line is also rotated by applying the rotation formula to each of the endpoint and join the line between join these endpoints. You will get a new line after rotation. So not a point only rotated, but you can also rotate a line. How? Now you know that the line has two endpoints. So you know that how to rotate an point. So there are two endpoints. So you now rotate that these two endpoints of that line. So after rotating a specified angle theta and with respect to a pivot point, you will get a two new location of these 2 points. You rejoin or redraw that point, join those points, and it is the specified output. Similarly, a polygon is also rotated by applying the rotation formula to each of the vertices like translation, and you rejoin or redraw these polygon using the new vertex coordinate. So in this way, a point, a line, and a polygon can be rotated like a translation. A polygon can be, suppose if you have to rotate a triangle, there are 3 points, 3 vertices of a triangle. So you have to apply the rotation formula each of the 3 vertices. So after you rotate the 3 points in a new location, you have to rejoin them. You will redraw this point and you will get your desired output. It is not required. This is a algorithm using a C program. So this is not required. So far we have discussed two techniques. One is a translation and another is what? Rotation. Now the third technique is scaling. The third technique is scaling. In translation, we shifted a point or shifted the image to one position to another position. In rotation, we rotate the an image from with respect to a pivot point in specified in direction, in specified degree of angle, either in clockwise or anti-clockwise. With some degree, 30 degree, 45 degree, 60 degree, theta will be any value. But what about scaling? What does the scaling do? Scaling is used to alter the size of an object. Sometimes it is required to alter the size, to manipulate the size, to modify the size. Suppose the size is too large, I require a smaller one, I can change it. If a size is smaller, I can enlarge it. So if you want to alter the size of an object, the scaling is used. Uh, Scaling, 2D scaling is performed by multiplying object position xy by scaling factors. Sx, it is a scaling factor along x-axis. Xy is a scaling factor with respect to y-axis. And the new coordinate of a particular point, suppose a point is at xy, the new point x dash y dash will be formed by the following formula. That is x dash equal to x into sx and y dash equal to y into sx. Sorry, sy. And in matrix form, you can write x dash y dash equal to sx 0, 0 and xy dot xy. That is, if you multiply those two matrices S and P, the first matrix is S, the scaling matrix, and P is the original location, and P dash is new location after resizing. After resizing, after to change the size, this is the new location and new position of that point. S if you multiply the two, you see SS into X, 0 into Y. You please recall the matrix multiplication formula, that you go to row wise the first matrix and column wise in the second matrix. That is x dash equal to sx into x plus 0 into y means 0. That is x dash equal to x into ss. Similarly, in place of y, 0 into x, sy into y. That means y dash is equal to y dot sy. And in matrix form, you can write p dash equal to s dot p, s into p. P dash is a dash y dash, S is equal to Sx 0, 0 and Sy, and P stands for the original location xy, which is a column matrix. You see here, any positive value can be used as scaling factor. Value less than 1, reduce the size of the object. If the scaling factor value Ss Sy is less than 0, sorry, less than 1, that is the size is reduced. You see here, there is a line of greater size. After scaling, we will get a line which has less size. So write your name. Those who have not written, write your name and the registration number in the board. Similarly, if the value is greater than 1, the size is increases. It enlarges the object. If scaling factor is 1, the size is not changed. So that is why scaling factor is 1 is you may avoid it. Because if you take the exact SS into 1, if you multiplied y into x 1, so you will get same y. So if the scaling factor is 1, the size of the object remain unchanged. If xs are equal to sy, if xs equal to sy, we call it uniform scaling. That is, we are changing the size of the object uniformly along x-axis and y-axis. If the scaling factor less than 1, then the object moves closer to the origin. You see here. If the scaling factor is less than 1, the size is diminishes, the size is decreases, and the object comes closer to the origin. You see, the object was the initial object with larger size, and you see the after scaling you will get a smaller size object, so it is closer to the origin. So if the scaling factor less than 1, then the object moves closer to the origin, and if the scaling factor is greater than 1, then the object moves away from the origin or farther from the origin. So we can control the position of the scale object by choosing the any fixed point x or y r. So x dash is equal to x into xs plus xr into 1 minus sy, and y dash other than origin, we can also make the transformation other than any point. Similarly, a polygon are scaled by applying the above formula to each vertex. Then the in previous example we reduce the size of one line. So a polygon are also scaled. You can also decrease or increase the size of a polygon by applying the above formula to each vertex. Then regenerating the polygon using the transform vertices. Then draw the lines among that polygons, because so polygons is nothing but it consists of some line. Polygon are selected by applying the above formula to each vertices, then represent the polygon using the transparent vertices. You know that polygon consists of some line. So we know that how to scale a line. So after this, we have to redraw or join the lines, and then you will get a new polygon with a new size. Uh, so far, we know that there is a matrix transformation is done using the 2D. So we are using only a two-dimensional matrix, and but here matrix representation and homogeneous coordinate. Let us see what is homogeneous coordinate. Many graphics applications involve sequence of geometric transformation animations, design and picture construction applications. We will now consider matrix representation of these operations. Sequence of transformation can be efficiently processed using matrices. Suppose we have to do the sequence of transformation. We have to at a time a translation as well as rotation, or rotation as well as scaling. So in this case, we need using the matrices, but the matrices may be homogeneous, that is square matrix. P dash equal to M plus P into M2, that is P, and P dash are column vectors. M1 is a 2 by 2 array containing multiplicative factors. M2 is a 2-element column matrix containing translation terms. For translation, M1 is the identity matrix. It contains 1 as the diagonal. For rotational scaling, M2 contains the translation term associated with the pivot point or scaling fixed point. To produce a sequence of operation such as scaling followed by the rotation, then translation. Suppose we have to want to make this first is scaling. and then rotation and then translation, we could calculate the transmitter coordinate one step at a time. A more efficient approach is to combine translation without calculating immediate coordinate values is multiplicative, and translation term of a 2D geometrical transformation can be combined into a single matrix if we expand the derivative by 3 by 3 matrices. It is easily can be calculated, easily can be combined in a geometric transformation if a single matrix is expanded to represent a 3 cross 3 matrix. That is a 2 cross matrix it was initially. Now if we expand it is a 3 cross 3 matrices. We can use the third column for translation terms, and also transformation equation can be expressed as the matrix multiplication. That means we can expand this. Let us see how we expand. Expand each 2D coordinate xy to 3 element representation xh y dot h is called homogeneous coordinate. H is the homogeneous parameter such that x is equal to xh by h, y is equal to yh by h. Infinite homogeneous represent for a point, a convenient choice to the choose is h equal to 1. If you change equal to 1, and you see here, you can compare now this translation matrix with the translation matrix we have already discussed in the first slide. Go to that. Suppose I am going to that directly. Where it was? Where? Here. You see. That is P dash equal to P into T. X into P plus T. But to this one, you see. There's another, that is x dash 1 0 0 1 t s t y x y, and 1 equal to 0 0 1. If we multiply, you see, if we multiply this matrix, you will get the same result. That is x dash is equal to 1 into x plus 0 into y plus tx into 1. That is x dash equal to s plus tx. Please recall the matrix multiplication. First matrix multiply the second matrix. The first criteria is matrix multiplication. The number of rows, number of columns of first equal to number of rows in the second. You see, the number of columns of first is 3 and the number of rows of the second is 3. So this matrix can be multiplied. This cannot be added, because for addition the matrix must have the same order. But this is the, you have multiplying this. That is x dash is equal to 1. You see, for only calculate for x dash is equal to 1 into x plus 0 into y plus tx into 1. That is x dash is equal to x plus tx, which was in the main formula. Similarly, y dash, you see, y dash means the second row and first column. 0 into x 0 plus 1 into y y plus ty into 1 ty. That is y dash equal to y plus ty. Then come to third one, 1 equal to 0 into x plus 0 into y plus 1 into 1. That is 1 equal to 1. That is, I have only added the third row and third column. T ty 1 0 0 1. So this representation is known as homogeneous coordinate representation. That is matrix representation with homogeneous coordinate. You see this one, the rotation matrix, and compare this matrix with the previous matrix. This matrix. Here results are cos theta minus sin theta cos theta. And compare this with this new matrix. The same is there. Cos theta minus sin theta cos theta, but I will expand it 0 0 1 0 0 1. In row and column I added 0 0 1 and 0 0 1. So this is your matrix homogeneous coordinate. Okay. So similarly scaling. Okay. So inverse translation we'll discuss in the next class. So I think I have not sent this transformation matrix to you. So I will send it to today the translation matrix. So please wait. I have take a snapshot. Please write your name and roll number or registration number in the board for the attendance. Those who have written, do not repeat. So those who have not written, please write your name